Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video we're going to be exploring some interesting concepts involving general chemistry, specifically involving periodic table trends and applying this into a specific species and how this species is going to actually lay the groundwork for how increase in size relates to various properties that this species exhibits as you go in terms of oxidation and reduction on the other side of the creation of ions. So please don't forget to hit the like, share and subscribe, by that way all got those can actually get the chance to check out these videos, and also subscribing is free. So let's dive into this particular question that actually tells us to rearrange the following calcium species in terms of the increase in size. And you're like wondering, what are the calcium species that we are going to be dealing with? Don't worry, it's not going to be involving isotopes. It's going to be mainly involving change in the number of electrons, and you want to be aware of that. So in this particular part here, what if you're given calcium species that are as follows? We have calcium atom, and then we have calcium plus ion, and then calcium 2 plus ion, and we have calcium 3 plus ion, and next is calcium -1, and finally we have calcium -2. And the big question here is how we're going to start off with this particular question. And first is you want to create a plan. What should I do in order for me to start off and move on gradually? So to start off, we need to go to the periodic table. First off, look for calcium, and once you figure out where calcium is, you notice that you go to the group, which is in this case group 2, and once you move to the steps, which are the periods, you should consider that to be 1 when you go to hydrogen, next is lithium, and then sodium, that is period 3, and then next is 4. So period 4, we can actually find the particular atom, which is in this case calcium, or I would say element. And so looking at specifically the element, we know that, hey, looking at the specific numbers, we know that our Z is represented as 20 and our A is represented as 40. And so once you have this taken care of, we are now going to define 40 as the indeed mass number, because we are going to be considering the isotope, which is calcium 40. There are other isotopes of calcium, but for the purpose of this particular video here, we're going to mainly focus on the Z value, which is 20. And so what does the Z value tell us? The Z value tells you, 1, that the number of protons is actually equal to the number of electrons. And so once you have this actually taking place and analyzed, then we can actually move further to have our next fundamental idea about what makes one subatomic particle important in chemical reactions compared to the other. Protons, they don't really make a huge impact. They do not, except when you're dealing with how easy it is to lose electrons. That is where protons comes into play. But in terms of chemical reactions from one atom to another, transfer of electrons is really a huge deal, and you need to keep in mind about that. So once you have that taken care of, we need to be able to then focus mainly on the protons, and later on look at the big player involving the change in the oxidation numbers of this calcium. So we're going to draw a line, a straight line, and this straight line will guide us through various different species and where they lie, depending on how you're going to define all these species. So at the middle of the aisle here, we have calcium atom, and our calcium atom will have number of protons to be equal to 20, and it actually applies to all other species around the calcium line. So you want to keep that in mind for the number of protons. However, the number of electrons will be, in this case here, equal to 20, but then as you move from left to right, where you're going to more positive values in here, or from right to left, where you're going to deal with negative values of the oxidation number related to calcium, we're going to see some interesting things and behaviors when it comes to that in this particular case. So Looking at this here, we're going to actually determine what our electronic configuration based on the quantum association actually leads us to conclude. We know that for the highest energy level of calcium, it is actually defined as the 4s, and the 4s actually has 2 electrons present in there already. Now, this is going to lay groundwork for losing of electrons, and depending on what next level or the level before that, that is going to depend on what is happening to calcium, whether it's losing or gaining electrons. In this case here, when you're moving from left to right, it means that we're looking at next is what if calcium loses 1 electron. In this case here, we are actually come to the conclusion that since the number of protons are the same, the number of electrons will be indeed different. In this case, it actually lost 1 electron, therefore it has 19 electrons, and so the highest energy level that is going to be present now is the 3p, and the 3p will have, in this case, 6 electrons. That is a maximum that it can allow. And so our 4s, take note here, there's still 4s, and we are taking 1 electron out. So instead of 3p, 6, take note that it is 4s1. So you want to keep that in mind. So when you're thinking about this, you want to think thoroughly that, hey, am I dealing with 4s still or 3s? Well, indeed 3p, but in this case, we're still dealing with 4s. So 4s1. And so once you have this taken care of, the next one is, what if we have a calcium atom losing 2 electrons, and so therefore it actually increases its oxidation number to 2+. Therefore, it now has 18 electrons, which satisfies its stability in terms of the electron state, because it wants to be like the nearest particular halogen, not halogen, noble gas. And so in this particular case, we are going to have our electron configuration highest energy to be, in this case, 3p, and we have 6 electrons right there. And finally here, we are going to look at calcium when it loses 3 electrons. This is really hard to pull off, and this will actually look like its nearest halogen, and in this case it would be, in this case, looking a little bit like calcium, but calcium will have the same size as the chlorine, but with chlorine have the same size as calcium 3+. Something to think about. And in this case here, it will have the highest energy. In this case, the energy is S, so the 3p5. And so once you have this taken care of, we can now look at what is happening in this particular case right here. As you notice, you're moving from left to right, which means that this is actually happening where we actually have our calcium actually performing a form of oxidation process that results in the loss of some amount of electrons, and we are going to increase by the same number of electrons that was lost in terms of the oxidation number of calcium. So in this case here, once question mark is the same as a question mark for the oxidation relative to the number of electrons, it means that you have the neutral form at the initial end right there. So in this particular case, we have oxidation happening. Oxidation, I'm just going to spell that in full. And while on the other side here, moving from right to left, we're going to perform something differently, where we're going to have a form of a gain of electrons, where we have calcium atom. In this case, we'll have to gain some amount of electrons, and this will lead to the formation of a calcium, which will have an oxidation number which is an integer similar to or the same as the number of electrons, but in this case it will be negative. So therefore, in this particular case, going from calcium to calcium negative, it means that this will have electron count that is actually +1, which is in this case 21 electrons. And so therefore, in this case, the highest energy level will now be, in this case, 3d1, which leads it into the transition metal state region. And then the next one here is going to be, what if calcium loses gains 2 electrons? Therefore, in this case, number of electrons will be 22, and so it will be in the 3D energy level with 2 electrons present in there. So this actually shows you the number of electrons and also what energy levels those electrons are placed, and so therefore we can actually come to the conclusion based on the atomic size and relate it to the reason why the atomic size changes or the ionic forms changes going from atom to an ion. So in this particular part here, looking at calcium, we can actually notice that the atom for calcium, which we're going to consider as this particular shape, actually has protons to be the same all across the board. All across the board here, the number of protons are the same, but what is happening here is that the number of electrons are changing, and so therefore going from left to right, we notice that as the electrons as electrons decrease, we have in this case more shielding, where you have in this particular less shielding, which lays our particular protons to be attracted more to the electrons, therefore resulting in the collapse or the to the condensing of our space. Therefore, we are going to actually notice a decrease in the size of our specific atoms going into the ion. So therefore, in this particular part, as you move from left to right, we actually have a decrease in the size, because as the increase in the attraction between the protons and the electrons, because we have less electrons, this leads to a increase in the shielding, decrease in shielding. Therefore, we have more electrons influencing, we have more protons that is attracted to less number of electrons in this particular case right here. So the particular part actually leads us to the other phase, where if you're moving from right to left, what is happening? What we notice here is that, hey, as we add electrons, we actually increase shielding. Therefore, the outer level where the electrons are positioned will not feel the attraction between the proton, and as a result of that, that will lead to a diffused space that will allow our electron cloud to be more spread out, and therefore this will show an increase in the size of our ion as we go from our specific atom right here, which is calcium. So that's about it for this particular video, where you're able to actually analyze and, in this case, finally arrange our specific species of calcium based on the size and also considering the number of electrons. And in this particular part, we can lead to our conclusion that for an increase in the size, we can now reposition our specific calcium atoms and the respective ions in the following manner. We have calcium 3+, and in this part here, we're going into calcium 2+, and this is followed by calcium plus, then calcium atom, then calcium negative. Finally, we have calcium 2-. And so this increase in size is due to a result which we know is due to an increase in the electrons. The number of protons remains the same, therefore we have more shielding of the core electrons that prevents the outer electrons or the valence electrons from feeling the attraction from the proton. Therefore, the increase in the size actually results because the outer layer or energy level is actually more diffused in its state. So that's about it for this particular video. Hope you're able to understand this. Please hit a comment down below. Let me hear your thoughts about this. But that way I can talk to you all soon. Stay smart as always and believe in yourselves.